Very good. That's a very good observation. You could have, at this point right here, used a Pythagorean identity that says, we have two major Pythagorean identities. We have this one. How many of you remember that one? Yes? Any of you remember the others without looking at your formula sheet? Anyone remember the others? Okay. I'm going to teach you how to remember them without having to look at a formula sheet. No, it's not an Indian. It's actually, I'm going to do it this way. This is like a shorthand notation, all right? I'm assuming everyone agrees with this one. Sine squared plus cosine squared equals 1, right? That you got? Okay, to get one of, there's two other formulas. There's three total. To get one of the other ones, I want you to take that equation and divide everything by sine squared. Okay, so let's take this divided by sine squared. Sine squared over sine squared plus cosine squared over sine squared equals 1 over sine squared. So what's sine squared over sine squared? 1. What's cosine over sine? Cotangent, but you're squaring it. I have to write cotangent, sorry, cotangent squared. Equals, what's 1 over sine? Cosecant squared. That's one of the identities. 1 plus cotangent squared equals cosecant squared. Now I'm leaving out the x. There would be like an x here and an x here. Now if you want the other one, you take this original one that everyone has memorized and divide it by cosine squared. Okay, so take that and divide it by cosine squared. You get sine squared over cosine squared plus cosine squared over cosine squared equals 1 over cosine squared. Sine squared over cosine squared? Well, sine over cosine's tangent, so that's tangent squared plus cosine over cosine, 1, equals 1 over cosine is secant, but then squared. So tangent squared x plus 1 equals secant squared x. So the observation that was made was that this could be rewritten as, what, secant squared y would be tangent squared y plus 1. Did y'all see that? This could be rewritten as 1 over tangent squared y plus 1. Why would you do that?
Because then you want to have to solve it.
That's right. We knew what tangent of y was, right? I boxed it. It was right here. We had put tangent of y was x, right? That's what we had. So if I take tangent of y and that's x and I square it, I get x squared plus 1 and I'm done. Right? Now the reason I didn't do that is because what's valuable here is the reference triangle. Now sometimes you can avoid it, but it's a better skill to know how to build the triangle and create any trig function from that than to hope that this is something you have over here that you can get through an identity. That's my opinion. All right, we're good? All right, so now we are equipped with, we're done proving, okay? Now we're just saying, hey, we've got 6 new formulas. We should be able to take derivatives, but we should also be able to apply all the rules that we've ever applied to these new functions. So here we go. Examples. Let's find the derivatives of these. Y equals arc sine of the square root of x. What's the derivative of this? So what are you going to use to do this? This is chain rule and the formulas, right? The formula we just came up with. The derivative of arc sine of something should be 1 over the square root of 1 minus x squared. But is it x that we're plugging in? It's root x that's being plugged in. This is chain rule. Do you see what I'm saying? So what's going in here is root x squared. Times, now that's the derivative of arc sine of something. Now you go inside and you say times the derivative of root x, which is 1 over 2 root x. And we could do a little bit more here. That That would probably be okay. All I did was squared the square root, and that just became this x right there. I put it all together in one fraction. You could even put these two roots together into a single root and make it x minus x squared, if you wanted to. Because you would put the two roots together and the two insides would multiply together. So you distribute that x through. And then we'd still have a 2 down here. But I'm just showing you could do that. Is that all right? Any questions?
So whatever the argument is, that's what's getting squared or whatever you're saying?
Yes. Whatever the argument is what's getting squared. Exactly. How about, let me change it a little bit. How about this? This will be interesting. This will be really interesting, actually. What is the derivative of arc sine of cosine of x? All right, so it's chain rule, right? You've got to take derivative of arc sine of something, which is 1 over the square root of 1 minus the argument squared. So what's the argument? Cosine. Cosine squared x. Now times the derivative of what was in there, negative sine x.
But that radical is sine squared.
Yes. This right here, I made this problem just because of this. I wanted to make that happen. What is 1 minus cosine squared x? Sine squared x. So this is 1 over the square root of sine squared x times negative sine x. Hey, how about I put that negative sine x on top? Is that okay? Put it up here. Which is really just negative sine x over sine x, which is negative 1. Well, I'm taking the square root of something squared.
Okay, that's going to cancel itself out, right?
Yeah.
Okay.
Mm-hmm.
Oh, I know.
That's kind of weird, huh?
I wonder what the inverse of
Yeah. It would be very similar to this. I think it might be negative 1 again. I think it'd be negative 1. If I graph that function, what is it going to look like? If I graph this function, what is it going to look like? What is, now see, this is where you have to start thinking a little bit like a Cal 2 student. If the derivative of something is negative 1, right? The derivative of that is negative 1 all the time. What does that mean? What does that tell you about that function? It's a line. It has the same slope the whole time, doesn't it? It has to be a line. That can't be a line. Can that possibly be a line? No. No. We messed up, right? Arc sine of cosine of x. Is this going to be a line or not? What do you think? I think it's going to be a line. But what it's not going to be is a line on like a continuous line everywhere, because we have domain restrictions, because it's an inverse trig function. Whoa. Okay. We've got some issues. We've got some major issues. And the reason why we have some major issues is because there's a few things at play here that we kind of subtly shove under the rug here. If we're going to be talking about the inverse sine function, we can only be looking between where? negative pi over 2, and pi over 2, right? So if you go and look at this, pi is about 3.14?
Yeah.
Okay. So pi is about here somewhere. Pi over 2 is somewhere in here. And the negative pi over 2 is somewhere over here. So we're only looking at this part of the function. And it looks like on this side, it does look like a line, and it does look like the slope of that is what? Negative 1. But on the left side, it looks like the slope is what? Positive 1. The reason that's happening is because of this right here. That is actually not just sine x. It is the absolute value of sine x. And that's something that gets overlooked a lot. When you say square root of x squared is equal to x, that is true so long as x was positive. If x was negative, it's not that. Let me try and illustrate that a little bit better. What if I take the square root of 4 squared? Okay, so what's, this is square this first, you get 16, right? And then you take the square root of 16, you get 4, right? Okay, now what about this? What if I take the square root of negative 4 squared? Still 4? Agreed? So look, if this is x, right? If this is x, x squared square root, the answer was x, right? But here, if this is x, x squared square root was not x, was it? It was actually that, but positive. So technically speaking, if you allow x to be both positive and negative numbers, it's the absolute value of whatever was right here. And that's what happened right here. We didn't put absolute value, which is okay. Don't worry about it at this point. But that's why our graph, the slope is not always negative 1. On the other side, it's positive 1. All right, let's move past it. I don't want us getting bogged down on that. We definitely don't want to cause confusion. Oh. 20 minutes. Let's do a couple more. You only have about 5, 10, there's about 12 derivative problems in this homework set. So to practice is only about 12. Let's do this. Y equals square root of x squared minus 1 times cosine, arc cosine of x. Find the derivative of this. Well, if you want, you can write it down. Sure. It's a product rule. Okay, go ahead. See what you can get. Got it? No, I'm kidding. Where, this right here?
Yeah.
This?
That's the first one.
Product rule. Finishing off the product rule.
Oh, yeah, I knew that.
Actually meant to write this problem down a little different. I meant to make this a 1 minus x squared, but it's okay. We'll survive. So product rule, derivative of the first one is chain rule, right? Derivative of the square root of something, 1 over 2 roots of that something. Then times derivative of what's inside, which is just 2x. Then times the second function. So that's the first part of the product rule. Plus, the derivative of the second one, derivative of arc cosine of x, you have to look on your formula sheet, is this, right? That's it. That's the derivative of arc cosine x. You're done. Times the first one. There. Do these cancel? No, they don't, unfortunately.
Why is that?
They're off by a sign.
Yeah, it's minus 6. Yeah.
That's why I say I meant to write it down the other way. I meant to put 1 minus x squared because I actually did want that to cancel, but not happening. The most you could do here is you could rewrite this as minus. You could do one big root, and you could do x squared minus 1 over 1 minus x squared, like that. You could do that.
That should be plus. It should be, well, you put the, yeah, the bottom should be 1 plus x squared, shouldn't it? What's minus is because, yeah.
Do what?
If you pull a negative out of 1, I put,
I didn't pull a negative out. This negative is this one right here.
yeah, that's what
And I rewrote this over that.
I just mean when you were doing it.
But the negative on the outside and the negative and the 1 minus x squared on the bottom, wouldn't that make it 1 plus x squared?
I'm not sure where you're talking about.
Cosine, arc cosine x minus 1 over root.
That's fine.
I didn't see the negative.
Everyone's making it like that.
Oh, in the formula?
No, I saw it in there, I didn't see it.
I think in the formula they put it out front, right? They put it out front. I put it on the top.
Why I changed my policy.
Are there any questions on that?
Now, would you say that the one in the middle, the first one before you did the thing on the bottom, would you say that would be simplified?
This one right here?
Yeah.
This over here? No, I would cancel the 2's.
Well, besides that. Yeah.
Okay. X cosine inverse x over root x squared minus 1. I would do that.
And then the rest of it.
And then this right here. All right. That was a bad example. I wanted that thing to go away, but oh well. You can't have it the way you want it all the time. So you're just going to have to play with these, all right? I mean, I could sit here and do more and more problems, but it's just chain rule. You just have new rules. You have new functions to work with. I will do one. Let's see time. This one is interesting, I think. Arc cotan of, whoa. Yeah, is that what I want? Arc cotan of x minus the square root of 1 plus x squared. Chain rule. Okay, what is the derivative of the inverse cotangent? Negative 1 over 1 plus 1 plus the argument squared, right? The argument squared. That means everything you see there. X minus root 1 plus x squared. That argument squared. Times now the derivative of the argument itself. So parentheses, very good, because it's going to be 2 terms. Derivative of x is 1. minus the derivative of the square root of all that junk. That's just another chain rule, right? 1 over 2 roots of 1 plus x squared times 2x. That's the derivative of what's in the root. 2's can cancel. So I could have out here 1 minus x over root 1 plus x squared. That's this piece. And then over here, well, probably just leave this alone. But yeah, what would happen if I expanded that? It would actually get uglier. Yeah, because you're going to have a middle terms. So I'll just leave it. And you could take all of this, right? And you could just slap that whole thing up here. You could, because this is like its own factor. It could go on top of that.
What would you have with the negative 1 in front of it?
Yeah, you would have the negative out there. Okay. That's going to be it for 3.5. I want you to make, you do your homework there. We have 12 minutes, 13 minutes. I have enough time to introduce you to the next topic, all right? Just an introduction. If you want, you can just sit back, relax, and enjoy. But I will start this again next time we meet, which is what, Monday? So just pay attention, I guess. If it, don't be surfing your phone or anything like that, please.
That's 3.4?
That's 3.5 is done. 3.4 we are not doing. 3.6 we're skipping also. 3.6 we save for Cal 2. And the reason why we save it is because, all right, in pre-cal you had 6 functions, sine, cosine, tangent, right? 6 functions. We now know all the derivatives for those. We just introduced the inverse functions from pre-cal, right? Arc sine, arc cosine. We have 6 derivatives for those. The section 3.6 covers what are called hyperbolic trig functions. And that's the first time you'll see them. And there's 6 of them. So that you get derivatives for each of those. And then there's inverse hyperbolic trig functions. So there's 6 of those, and then you learn the derivatives for those. So in total, you have 6, 6, 6. You have 24 trig functions. Sine, cosine, tangent, inverse sine, cosine, tangent, hyperbolic sine, cosine, tangent, inverse hyperbolic cosine, tangent. And then you have 24 derivatives for each one. No, that's why we have formula sheets. But there are certain ones that are used a lot.
Why do they call them the antiderivative as opposed to an inverse derivative if it's just that does it?
Because we reserve the word inverse for functions. A function that undoes another function is called an inverse. And when you talk about taking a function and undoing the derivative is what we call a functional operator. It's different than a function. It's something that operates on functions. It's just a technicality. So we call it the antiderivative.
Sounds evil.
Yeah. Well, if you think the derivative is evil, then the antiderivative will be good. Right?
Antiderivative sounds evil.
Okay.
Yeah, it's like it's evil plan.
It is a evil twin.
All right. Let's see if you remember this. One. Right? This was the junk over junk formula. Remember this one? It's very, very important. I told you need to memorize this. It was in the video, the course videos. So please remember these 2 important limits. There's actually 2 of them, but this one we used a lot. The other one was this one. It's cosine x minus 1 over x. And that equals 0. I never proved to you why these 2 were true. I just told you that they were, right? I said just take it on faith. 3.7 is a section entitled L'Hospital's Rule. It's actually pronounced L'Hôpital. 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 L'Hôpital's Rule. And this is what we're going to spend all of next class on, and probably a lot of the next class also. So all of next week will be spent on 3.7. And the reason why is because this rule is really, I'm trying to find a word that would be not vulgar to describe how wonderful it is. It's what? Yes, that's what I would say. It is. So let's take a look at this limit right here.
Does it make life easier?
Oh, yes, it does. Okay. Now, I'm not going to give you L'Hôpital's rule right now. I'm not going to tell you what the rule is. I'm just going to I'm going to do it, and then you're going to be like, okay, sure, if you say so. I'd like for you to take this limit, and I'm going to tell you right now to just kind of wonder whether or not this is right. Is that limit the same as, just take the derivative of the top. What is the derivative of the top? So don't give me quotient rule right now, just separately. Derivative of top is what? Cosine x? Okay, now separately, give me the derivative of the bottom. 1. Okay, now let x go to 0 and tell me what happens. What is cosine of 0? 1. So the top is headed to 1, and then as x goes to 0, this doesn't change, right? And you get 1. And what is this answer? 1. What is the answer supposed to be? 1. I wonder if that's right, if I can do that. Like if I'm having trouble with the limit, we didn't talk about this, but if I let x go to 0, what was the problem here? What do I get if I let x go to 0? I get 0 over 0. But if I take the derivative of the top and bottom, I just got the answer, 1. I wonder if that was just coincidence, I got lucky, or if that's the way it is. Look at this one right here. That one. Okay, if I let x go to 0, cosine of 0 is 1. 1 minus 1 is 0, so I get 0 on top. On the bottom I get cosine, x is going to 0. That's just 0 on the bottom, right? 0 over 0 was bad. And what do? Well, let's try this. Let's just take derivative of top and bottom separately. Derivative of top is just what? Negative sine x. And then on the bottom is 1. Right? Derivative of the top is negative sine x. And then this is 1. Now let x go to 0. Sine of 0 is 0 over 1. What's 0 over 1? 0. That's what I told you it was going to be, right? Coincidence? No, it's not. How about this? No. Be careful. This has nothing to do with taking a derivative. We are trying to find limits right now.
So we'll go back to it.
And in this limit, I'm telling you take derivative of the top and bottom, and it's looking like the answer we're getting here is matching what I'm telling you it should be. Here's another example. X squared minus 4 over x, let's say minus 2. What would happen if I asked you to plug 2 in here? You get 0 over 0, wouldn't you? Now back in the day, the way you would solve this, and you remember what you would do to figure that one out? You would do the top as a difference of squares, and you'd factor it, wouldn't you? I'm going to do that on the side over here. This is the way we were doing it. You'd cancel the factors, wouldn't you? And now let x go to 2, and what do you get here? 4. The answer is 4. But I wonder if I could do what I just did a second ago. What's the derivative of the top? What's the derivative of the bottom? 1. Now plug in 2. 4? Now it's starting to get a little scary because it's looking like it's matching every single time, right? This is the beauty of L'Hopital's rule. This is going to work every single time. Yeah?
Can we use that?
So on the final. If I don't tell you how to find a limit, you can do anything you want. All right? Let's look at one that we had to work a little harder to get. Limit x goes to infinity. I'm asking you to go back in the day here. 3x squared minus x plus 1 over, let's say, x squared plus 4. If you let x go to infinity here, you would get infinity over infinity. And when you have infinity over infinity, it's kind of like 0 over 0. It was bad. Remember that? And so, does anyone recall how we would attack that one? Yeah, exactly. You would look at the highest power of x down here. You would come in with a 1 over x squared here, a 1 over x squared here. You would distribute it through like this, 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 and this, this, and then you would get things to go to 0. Hopefully that rings a bell. That's the way we were doing it. But I wonder if it would work this way too. So limit x goes to infinity of 3x squared minus x plus 1 over x squared plus 4. What would happen if I just take the derivative of the top and bottom? So what's the derivative of the top? 6x minus 1 over derivative of the bottom? 2x. Now let x go to infinity again. What happens? Infinity over infinity. Ah, that didn't work. But let's try and do it again. Take derivative of the top. Over 2, which is 3. Well, that's exactly what we would have gotten had we done this. If you had passed that through, you would have got here a 3 minus, and then here, 1 over x, and then here to here, 1 over x squared. And then over here, you would have had this and this would have been a 1, and this would have been 4 over x squared. And now if you let x go to infinity, fixed over infinity, fixed over infinity, fixed over infinity, those all go to what? 0, and you're left with 3 over 1, which is 3.
So is that like y double prime over there?
Nope, nope, we're not looking at it. That's why you have to be careful with this section. This section, what we're doing is we're going back to limits. All right, we're going back to limits.
So this is like our product and chain rule of derivatives for limits.
We're not doing any product or chain rule here. We're taking derivatives.
It's equivalent to a shortcut.
It's shortcut, yes.
So it's basically just brute forcing it until it works.
What did you say? Brute forcing? That's brute force?
No, that's just like doing it over and over again until we can get it to.
Well, we're going to have to get into like, there are certain times we can't use this, all right? What I'm trying to get you to like a sneak preview of is the fact that a lot of the limits that we've done, we are now going to have an easier way to get them. And a lot of students get really upset when they see this. They're like, well, why didn't you show that to me in the beginning? You know, like limits would have been a lot nicer had you not just shown that to me in the beginning, right? Right? Do y'all feel that way a little bit? Well,
At this point.
I think it's a good feeling to have that, you know what, you should show me this is easier, but please pay attention. We started with this class with the limit, didn't we? And what did we do from that? We defined the derivative. The derivative was a limit, right? I'll just say f prime. We defined a derivative. And now what I'm doing is I'm going backwards and I'm going back to limits. And I'm using the derivative to actually find a limit, right? If I would have walked in here on the first day when we started limits and said, hey, look, see that everyone? X is going to infinity, infinity. What do? Oh, take the derivative. You would have been like, what? What's a derivative, right? You wouldn't have known that that's 6x minus 1 over 2x. So we couldn't do this earlier. So this is actually what makes L'Hopital's rule so great. He was a mathematician, is that he found a way to use the derivative to go back and solve harder limits. So it's like an application of derivatives. One application is that we can use them to solve limits. Okay, that's it. Have a good weekend. Do your homework.
Do you want them to name a rule after you now?
No, I haven't done anything worthy of a rule.